Okay, guys, last week you learned how to draw a Punnett square and the fact that circles represent females, squares represent males. Shaded in figures represent that the person in that pedigree has the trait that you're talking about, and non-shaded in shapes represent the person does not have that phenotype, that trait. Okay, so today I want to go over two examples with you of how to analyze a pedigree and determine individuals' genotypes. Okay, so the family tree that we're looking at here is for having a white lock of hair. So any of the individuals that are shaded in that like bluish purple color have a white lock of hair, and the individuals that are the white circles or squares do not have a white lock of hair. Okay, so we're going to start at the first generation, which is at the top. The grandfather, which is the square at the very top of the picture that's shaded in, he has the trait, because again, you can see it shaded in, and we are going to assume that this trait is dominant. You know it's dominant because if you look in all three generations, you find the trait. If the trait skips a generation, that tells you it's recessive. But since this one's found in all the generations, we know it is dominant. Now, we are going to use W's for white because it's a white lock of hair. So if anybody in this family tree pedigree that is shaded in is going to automatically have which letter? If you look, they automatically have to either be homozygous dominant, so two capital W's, or they have to be heterozygous with one capital W, one lowercase w. So I know that every single individual in this tree, you can see all these people that are shaded in, they have to have a capital W. Okay, so I'm going to go through. If you look, I'm adding W's to each one of those shaded in people. I know that automatically. Now, they have two letters because they have one gene from each parent. We're going to go back and figure out their second letter in a moment. Now, everybody in this tree that is not shaded in, that is white, is automatically homozygous recessive because remember, this is a dominant trait. These people don't have the white lock of hair, therefore they must be homozygous recessive. So if you look at the pedigree down below, I added in a bunch of little W's next to individual 1, 5, 7, 9, and 10. By the way, I added those numbers. They're not going to be in your notes. I just added them so I can discuss them while I'm explaining this video to you guys. Okay, now my last goal is I have to go through and I have to figure out the other individuals. 2, 3, 4, 6, 8, 11, and 12. If you notice for each one of those shaded individuals, I know they have a capital W, but I have to figure out, are they homozygous dominant or heterozygous? Okay, so if you look at let's look at individual number 4, for example. If you look, we need to figure out that son, number 4, he's the son of number 1 and 2, his second allele, his second letter. If you look above, the mother, the grandmother, who's number 1, she's homozygous recessive, which means she has two lowercase w's, which means we know for sure she has to give one of those two letters to each one of her kids, to 4, 5, and 6. Number 4 and number 6, who have a blank space, they automatically have to get a little w because it came from their mother, who is number 1. I'm going to fill that in a second. I'm going to go back over to 3 first, and then I'll go to 4 and 6. If you look at number 3, we don't know number 3's parents. They're not in this pedigree, but we do have some information if you look down below. If you look down below, 8 and 9 are 3 and 4's kids. If you look at number 9 has two lowercase w's. He or she had to have gotten one of those from the mom and one of those from the dad. So that means, if you look, I'm going to start filling them in. We know that number 3 and number 4 have to be heterozygous. They have to have one of each of the letters because number 9 has two little w's. That means 3 and 4 had to have each carried a little w. By the way, I just realized I skipped number 2. Number 2, who is the grandfather in this case, we know has to be heterozygous because if you look down below at number 5, look at number 5. Number 5 has two lowercase w's. One of these came from the mom, who's number 1, and one of them had to come from the dad, who's number 2. Okay, so number 2 had to be heterozygous. Okay, let's go over number 6 now. We're going to use the same reasoning. Looking at number 6, look at number 6's mother, who's number 1. She has two lowercase w's. That means we know for sure number 6 has to be heterozygous. We could have also determined if you looked at number 10, who is her son. Number 10 has two lowercase w's. One of those had to have come from number 6. Okay, I'm going to go over to 12 now and then go back over to 8. So 12 and 11. 12 and 11 are both in the same scenario here. They both have the white lock of hair, but we need to figure out their second letter. Look at their father, who's number 7. He has 2 lowercase w's. He has to give one of those letters, which is automatically lowercase w, to each of his 2 kids, or each one has 3 kids down below. So 11 and 12 have to be heterozygous. Okay, the last one I want to talk about is number 8. Look over at number 8. Number 8 we know is a white lock of hair, so it's a capital W. But the question is, what is the second letter? Let's just pretend that mom, who's number 3, gave the capital W to number 8. What did dad, who's number 4, give to number 8? Did he give a capital W or lowercase w? The answer is we don't know. We cannot be sure unless we get genetic testing done or we have more information, like if this woman goes on to have some kids and we can analyze her kids. So if you notice number 8, I put a question mark there. So one W, one capital W, and then one question mark. I don't know what the second allele is, so I don't just make up a guess. I have to put a question mark. It's either a capital W or lowercase w. We are not sure. Okay, so let's do one more example, this one for albinism, which is people who are albinos. So first off, if you look at this tree, the people that are shaded in black in this example are going to be albinos, and the people that are kind of bluish are going to be normal people, normal skin pigmentation. So first off, is this a dominant or recessive disorder? If you look at all 3 generations, if you notice generation 1, they don't have the trait. They are not albinos. Therefore, we know because every generation doesn't express the trait, this is a recessive disorder. Okay, so let's start with making a little code. We are going to use A's as examples for albinism. A capital A is going to be a normal allele. By normal, I mean your normal skin pigmentation. If you have a capital A, you are not an albino. Okay, lowercase a is the recessive allele for albinism. The only way you can be an albino is if you have 2 lowercase a's. Okay, so if you look down below at the pedigree, by the way, I want you guys to be filling in these letters as you do your notes. So actually, I want you to write the genotypes underneath the symbols on each one of the pedigrees in your note packets. So I know that the individuals down below that are shaded in black, which you can see, I've already filled in 2 lowercase a's. We know they're homozygous recessive since they're albinos. The only way to be an albino is if you have both recessive alleles. Now, using the same logic, I automatically know that everybody else that is kind of shaded in blue, we know they have to have at least 1 capital A because they're not albinos. That means they're either homozygous dominant or they're heterozygous. Let's first start by trying to figure out the grandparents who are in the first generation at the top. We know they have to have 1 capital A because they're not albinos, but then we can go even further and we know that they're heterozygous, meaning they have a lowercase a as well, because if you look, they have 3 kids, who is this square, and this circle, and those 3 kids have albinism. Notice they have 2 lowercase a's each. One of them had to come from the mother, one of them had to come from the father. So I'm going to fill them in. I know that these 2 people are heterozygous based on their kids. Okay, so I now went through and I added a capital A to everybody else on the pedigree because they're not albinos. They have to have the dominant allele. Okay, so now we're going to go through and we're going to try to figure out each person's genotype. Okay, so I'm going to just start down here. You can see they're numbered 1 and 2. They're not numbered in your notes, but I just numbered them 1 and 2 just so I can refer to them. We know that number 1, who's this woman right here, has to give a lowercase a to each one of her kids who are in the bottom right hand of the pedigree. Because she has 2 recessive alleles, one of those recessive alleles has to go to each one of her kids. So notice I added a lowercase a to each one of these kids in the bottom right hand corner. Now, number 2, who's the dad of all these kids, we know the dad had to have given a capital A to each one of the kids because each one of them is not an albino. But the question is, what is his second allele? To be honest, we cannot 100% sure figure it out. Since he has 2 alleles, we know he gave a capital A to all the kids. So he has 6 kids, which is a lot. So the chances are he has 2 capital A's because you have a 50% chance of giving each letter each kid. So if this guy was heterozygous, meaning he had a lowercase a here where the question mark is, it would have been very highly improbable that this scenario would have come out. He probably would have had an albino kid or two, or actually three, because it would have been half of them, approximately. So we don't actually know for sure, so we're going to leave that one as a question mark. Okay, so normal father could be either heterozygous or homozygous dominant. We just don't know, so leave it as a question mark. Okay, now, both of the original parents are heterozygous, as we said, so now we can go through and we can just start filling in everybody else. You can see it, we're going to start filling them in. Let's look at these two kids that have, these three kids, I should say, that have already added the question mark to. If you look at, let's say, this son right here, this son is from the two original parents. We know he has a capital A because he's not an albino, but we don't know what the second letter is. The dad could have given either capital A or lowercase a, so we aren't sure. We don't know because he has no kids. This woman, same boat. We know is capital A because not albino. She's not an albino, but we don't know the second allele. Okay, now let's look at this person over here with the question mark. It's the same scenario. Or is it? Because we know that now this new number one over here, she gave a lowercase a to each one of her kids, or sorry, to these two kids who are albinos down here. So we know that number one in this picture has to be heterozygous because she has two albino kids. And using the same logic, number two, who is an albino, had to have given one lowercase a to the square in the bottom left and the circle down here at the bottom as well. So systematically, if you go through, you can start figuring out what each person's genotype is. It takes a little bit of work and a little bit of practice, but eventually you guys will get better at it. There are sometimes people you cannot figure out their full genotype, so you have to leave them with a question mark if you cannot figure out the second allele.